Hello, good morning, everyone. My name is Imran. I'm a PhD student at Florida Atlantic University. For the last 4 years, I've been working with this emerging standard at MPEG AI. I actively participate with them. So in today's talk, I'm going to give some brief overview of this standard and some performance evaluation. So the first thing is the problem statement. The problem statement is that a camera captures a video and the end user is not human. In this case, it's machine. So the very obvious solution that we could do is that we run the deep learning model on device. But in this era of deep learning, there are many network which has like billions of parameter, and it's not possible to run this network on device locally. So the second approach, what we could do is that we capture the video, we compress it, we send it to the remote cloud, and on the cloud we have like high GPU, high computing power. We run the network there, and we get the inference results, which we send back to the edge device. But if we do that, then there is another problem, which is that your sensitive data is going to the remote server. And the second problem is that you are not fully utilizing your edge device. In most of the modern device, you have NPU and GPU accelerator, but you are only doing encoding, so you are not utilizing that fully. So there is this another approach, which is I call it best of both worlds. Here, what you do is that you cut a neural network into two parts. And you put one part into the edge device, and the second part into the cloud. Now, by doing that, the problem statement become like different. This is because now you are not sending raw videos data. What you are sending, the stream, is a features. So it also gives you privacy protection. This is because it's not direct raw image that you are sending from your edge device. And it also gives you the capability of doing compute offload. So compute offload means if your edge device support some part of the neural network computation, then you can run it on your edge device, and you delegate other tasks to the remote server. So when when you have to compress this feature, you have like the one naive approach. In this naive approach, what you do that you get this feature which are in like 32-bit floating point, and you convert those to 10-bit. Then you pack those 3D to 2D packed frame. Then you push it through the video encoder, and you stream it. So just to give you an example, this is how it looks like. So this is the original image. Then you get the feature tensor, which are in 3D, but you packed it into 2D format, and you convert this 32-bit to 10-bit. Then you push it through the video encoder, and you stream it. As you could see that it also gives you some privacy protection. That's because you can't tell what's inside of these features. But the problem here is that the features, they are very large. It's like a huge amount of feature. So in order to efficiently transmit these, you need some kind of a codec here. So that's where the MPEG comes in. In 2019, they started this standardization process, which is MPEG AI Part 3 and Part 4. I'm going to be describing some of the tools from there and some performance evaluation. But the good thing about this feature is that they have lots of redundancy. Like you can reduce this redundancy by a lot, even though it seems like it's like 21 times larger than the original image. But there is lot more scope to compress these things efficiently. So just to give you an overview, so the MPEG AI, so the first option that we have is edge inference, which is very obvious one. You run it on locally, but if you do, then you don't have compute offload, and sometimes your device doesn't support the whole computing thing. The second thing you could do is the VCM, video coding for machine. You compress the video, you send it to the cloud, you run your inference there. But if you do that, there's a privacy risk, and you can't do compute offload. The third approach, the best of both worlds, which you do split the network, you put two parts in two places, and you have a codec inside there. So I don't have enough time to go into the details of all the coding tools. I'll just give some brief overview. But if you're interested, interested, please let me know. I could describe later. Um, so the first tool we have in the video coding for machine, the MPEG-AI part 3, in this standard is the temporal resampling. In a video, you don't need all the frame for the machine task. That's because in consecutive frame, there are same kind of objects there. So you could drop some of the frame in the middle. Then you have a spatial resampling. Unlike traditional video coding, you don't need to preserve the full resolution. You could like downsample it, downscale it, but even at the end task, the machine task could be the same. Then there is the third one, which is the ROI processing, where you keep the object of interest in like high resolution, but for the background and other stuff, you just make it like more compressible to reduce the bandwidth. Then there is another thing which is bit depth truncation. You don't need full bit depth precision. This is because these end network, these neural network, they don't care about like how good looking the picture is. All they care about is there a feature enough to identify the object. So you can do also some kind of bit depth truncation. And encoding is like, it's traditional, you could use HEVC, AVC, VVC, anything you want. And for the decoding process, it's the same, you just undo the operation. So now this is another standard which was I'm saying like the feature coding for machine. Here you don't send the images, you compress the feature, which are kind of like a 3D tensor, and you input that to the codec. So it's very different from all the codec that we know. It's a 3D tensor that we input to the FCM. So this is the diagram, like very brief overview of that. So here we have a couple of modules. First one is the transform. So this transform is actually a neural network. And the way that the standard is defined, you can design your own transform. You can design your own bottleneck here. That would that will remove the redundancy from your features. Then you have channel pruning. It has been observed that most of the channel from this deep learning network, they are not activated all the time. So based on some criteria, you could actually truncate some of those channels. Then you need to do packing. That's because traditional video codec, they support 2D. So you pack those channels into 2D. Then you have another module, which is conversion, where you transform your floating point 32-bit to 8-bit or 10-bit. And as usual, you have the encoding. And for the encoding, you could use any encoder you want, HEVC, AVC, or PVC. And for decoding, you do the opposite of it. So I'm going to now give a brief overview of some of the common tools that applied in two places. So the first one is the global statistic preservation. Here, the idea is that when you go to feature domain, it's much more resilient to noise. So you can like quantize heavily, but you still have like good performance at the end. So here, I will skip over the math mostly. Here, the idea is that you have a feature tensor on the encoder, and somehow you assume that there's a Gaussian distribution, and you pass some parameter to the decoder, so the encoder and decoder will have same kind of feature. Just to say it simply, it's gonna be like at the corner, you could see like, it just tries to like align both distribution on both sides. Maybe in like traditional video codec, we don't need it, but for AI task, it's very important. Then we have another tool, which is LCR. We have a full paper on it. I'm not gonna go into the details of the full algorithm, but just to say it simply, what it does is that when you prune those channels, you remove some of the channel because you want to reduce the bandwidth, you have to also communicate that which channels you are removing. That become a mask, and sometimes this bit mask is expensive to send to the decoder. So here it provides a way to send a signal or rank, so the decoder could infer all those data. So now for the performance evaluation, it's very hard to compare two standards together. That's because every standard optimized for something. But here I took the common test and training condition from the both standard, which are common. And here you could see there are two tasks are in consideration: object detection and tracking. And we have a couple of network here. Here the baseline that I'm going to be comparing with is the first one is the edge inference, the very obvious one. You run the whole AI on your device locally, no transmission. The second one is the remote inference, which is the traditional way without the standard. Right now, the way you will do it, like you would use a VVC encoder there. And I will compare the VCM and FCM with those paradigm. And we took the feature coding test model, the latest one, and also the VCM reference after the latest one. And here we have rate of accuracy plot, not rate like the traditional one. So in the y-axis, what you are seeing here is the MAP, which means accuracy. That's because for the machine task, it matters like how much is your accuracy was. And here the orange curve that you are seeing, that's for FCM, the feature coding, where you are compressing the feature. The blue one, that's the traditional way, like without the standard, the way you will do. And the bottom one, the small, that's the VCM, the video coding for machine. Now, as you could see that the FCM achieved the same accuracy compared to the remote inference with 90 to 95% bit rate reduction. But somehow the VCM video coding for machine for this task, detection task, does not work that well. Similarly, I have the rate accuracy plot for tracking task, where your end task to track different object. And in tracking task, you can achieve much more higher bit rate reduction. That's because the redundancy between those frames and the features are very high. And you could see that both FCM and VCM, they are on the top left. So with like very low amount of bit, they are achieving some high accuracy. And the dotted dash line that you are seeing, there's the edge inference. So if you don't do any transmit, that would be your upper bound. But you could also observe that some of the codec is achieving more than that. Theoretically, it's not possible. And the reason that it's like that is because there are some study that this compression somehow help the end task accuracy of this deep learning network. So we also test like how efficient this VVC could be for feature coding for machine. This is because if you think about it, like for the last couple of decades, we are working on this video codec. This is purely for human. There is no optimization for machine. And of course, some of these things gonna be suboptimal for this codec. As you could see that the block partitioning and the interpretation, these are not fully optimal here. So that tell us to like, what if we don't use VVC, we use something else, like you go back to older codec like HEVC, ABC. And as you could see, the first column highlighted is the HEVC, and the bitrate loss is 1.39, which is contradictory with the traditional codec, right? Like in traditional codec, when you go HEVC to VVC, there's a 40% improvement, at least like. But here, it does not show that much improvement, and it's expected just because this domain is completely different. It's features, it's not images. But if you go AVC, for detection, there is some loss, 50%, 40%, which is quite significant. But if your end task is TVD tracking, like tracking kind of task, then you could still use AVC. So just for a conclusion and takeaways, what I could say is that both this VCM and FCM works well compared to the tracking task with the remote inference, the VVC. And FCM in some cases shows like around 96% bit rate reduction on these cases. And the interesting thing is that you don't need like the VVC to use these standard codec. That's because you can still go to AVC or HEVC and have on-par performance if you don't want to adopt PVC right now. So that's all. Thank you.